What if we told you that there's a whole other universe hidden from plain sight? A world of celestial objects and mind-bending phenomena that can only be seen through the lens of infrared technology. Join us on a journey through the cosmos as we explore the universe in infrared and uncover its hidden mysteries. Don't miss out on this captivating adventure. Watch now, and let's explore the cosmos together. The technology used to see the universe by infrared. Spitzer Space Telescope. The Spitzer Space Telescope, one of NASA's great observatories, was launched in 2003 to explore the infrared universe. It was sent into a solar orbit, trailing just behind the Earth and gradually drifting away from it. The telescope had three cutting-edge focal plane instruments: the Infrared Array Camera, IRAC, the Multiband Imaging Photometer, MIPS, and the Infrared Spectrograph, IRS. At the end of the cold mission in 2009, when the liquid helium coolant was exhausted, Spitzer entered its warm mission phase. MIPS and IRS stopped working, but two of the four cameras in IRAC persisted with the same sensitivity. In 2016, the Spitzer warm mission was extended into its beyond phase, and in 2020 the mission was terminated. Infrared Array Camera, IRAC. When Spitzer was launched, IRAC provided a significant advance in the capabilities of space-based detectors, both in sensitivity and in area coverage of the sky. IRAC is a 4-channel camera that provides wide-field images over a range of 4 near and mid-infrared wavelength bands. The 2 near-infrared wavelength bands are observed by indium antimonide array detectors, 256 x 256 pixels, and the 2 mid-infrared wavelength bands by arsenic-doped silicon array detectors, 256 x 256 pixels. Why is it good to study the universe in infrared? The James Webb Space Telescope, Webb, will observe the universe in the near-infrared and mid-infrared, at wavelengths longer than visible light. By viewing the universe at infrared wavelengths with an unprecedented sensitivity, Webb will open up a new window to the cosmos. With infrared wavelengths, it can see the first stars and galaxies forming after the Big Bang. Its infrared vision also allows Webb to study stars and planetary systems forming inside thick clouds of gas and dust that are opaque to visible light. The primary goals of Webb are to study galaxy, star, and planet formation in the universe. To see the very first stars and galaxies that formed in the early universe, we have to look deep into space to look back in time, because it takes light time to travel from there to here. The farther out we look, the further we look back in time. We need to shift to another light. The universe is expanding, and therefore the farther we look, the faster objects are moving away from us, redshifting the light. Redshift means that light that is emitted as ultraviolet or visible light is shifted more and more to redder wavelengths, into the near and mid-infrared part of the electromagnetic spectrum for very high redshifts. Therefore, to study the earliest star and galaxy formation in the universe, we have to observe infrared light and use a telescope and instruments optimized for this light like Webb. Star formation in the local universe takes place in the centers of dense, dusty clouds, obscured from our eyes at normal visible wavelengths. Near-infrared light, with its longer wavelength, is less hindered by the small dust particles, allowing near-infrared light to seep through the dust clouds. By observing the emitted near-infrared light, we can penetrate the dust and see the processes leading to star and planet formation. Objects of about Earth's temperature emit most of their light at mid-infrared wavelengths. These temperatures are also found in dusty regions forming stars and planets. So with mid-infrared radiation, we can see directly the glow of this slightly warm dust and study its distribution and properties. Of particular interest is the infrared part of the spectrum, which extends from the red region of the optical spectrum to the microwave region of the radio region. The infrared spectrum is of particular interest because it yields information on the following components. Most objects are too cold to be observed in visible light and radiate primarily at infrared wavelengths. The early universe. Due to the expansion of the universe, visible light emitted by stars and galaxies in the early universe is shifted into the infrared spectrum. Infrared radiation is therefore important in observing the birth and evolution of the first stars and galaxies in the universe. The dusty universe. Dust in the universe absorbs ultraviolet and optical light and re-emits it as infrared radiation. Therefore, infrared radiation is important in mapping the distribution of dust in the universe. Infrared radiation can also penetrate clouds of dust. Thus, protostars that are being born in the center of dense clouds of molecular gas and dust can be observed at infrared wavelengths. The chemical universe. Many atoms and molecules radiate primarily at infrared wavelengths, yielding information on the chemistry of the universe. In particular, organic molecules associated with living organisms radiate in the infrared. Infrared radiation is important in searching for evidence of life in the universe. Infrared radiation can be observed from the surface of the Earth only through a few atmospheric windows at near and mid-infrared wavelengths. The Earth's atmosphere absorbs most of the spectrum. Therefore, to observe the entire infrared spectrum, space telescopes are required. What's out there giving off infrared light? Infrared astronomy helps observers peer into regions of space that would be invisible to us at visible or other wavelengths. For example, clouds of gas and dust where stars are born are very opaque, very thick and tough to see into. These would be places like the Orion Nebula, where stars are being born even as we read this. They also exist in places like the Horsehead Nebula. The stars inside, or near, these clouds heat up their surroundings, and infrared detectors can see those stars. In other words, the infrared radiation they give off travels through the clouds, and our detectors can thus see into places of starbirth. What other objects are visible in the infrared? Exoplanets, worlds around other stars. Brown dwarfs, objects too hot to be planets, but too cool to be stars. Dust disks around distant stars and planets, heated disks around black holes, and many other objects are visible in infrared wavelengths of light. By studying their infrared signals, astronomers can deduce a great deal of information about the objects emitting them, including their temperatures, velocities, and chemical compositions. In conclusion, the universe in infrared is a truly mesmerizing sight, revealing hidden mysteries and shedding light on some of the most awe-inspiring phenomena in our cosmos. From the birth of stars to the collisions of galaxies, infrared light captures it all. So if you're looking for a truly mind-blowing experience, don't hesitate to explore the universe in infrared. Who knows what new wonders you might discover? So, what are you waiting for? Grab your telescope, head outside, and start exploring the vastness of the cosmos today. If you enjoyed the video, kindly subscribe to our channel, or you will miss our